Hi, in this final lecture on the blood, we are going to be talking about hemostasis, clotting, and homeostatic imbalances. So hemostasis is the process that stops bleeding. So the hemo part of hemostasis, that refers to blood, and stasis is referring to the fact that we are halting or stopping that process. So we are stopping the bleed. This prevents loss of blood from even small blood vessel breaks, and this is essential for survival. Without it, even minor cuts could lead to life-threatening blood loss. So normal conditions, when blood vessels are intact, blood flows smoothly because of the endothelium that allows the blood to go through there. Hemostasis is going to begin here when you actually have a damaged cell wall. So characteristics of the response, so it is going to be fast. It's going to be localized to the injury site, and it's going to be tightly regulated. So fast, it's going to happen almost instantaneously. It's going to be localized. It's only going to be occurring where the damaged vessel is, and tightly regulated. You don't want this the processes that are leading to hemostasis to occur when this is happening. You don't want this to occur elsewhere in the body. So the regulation involves clotting factors, platelets, and the injured tissue cells. Three major steps to hemostasis. So we have platelet or vascular spasm, followed by platelet plug formation, and then finally coagulation. So the vascular spasm is the immediate response to vessel injury. It is when the damaged vessel undergoes vasoconstriction, which is going to reduce the flow of blood. So you can see here, compared to this over here, you've had the blood vessels constrict, thus reducing the amount of blood that's flowing through there. What triggers this? So this is triggered by a vascular smooth muscle cell damage, so direct injury to those cells. This is enhanced by chemicals that are released by the damaged endothelial cells surrounding it. So you have these cells responding. So you have the inner layer sending signals to the smooth muscle cells, causing them to contract. Can also be assisted by platelet factors. So these are activated and leading to vasoconstriction, and pain receptors can also lead to this. The vascular spasm is going to be effective and be based on the degree of tissue damage. So more damage means more vasoconstriction, and it is going to reduce blood loss for up to 20 to 30 minutes, which is crucial because this helps minimize the initial blood loss while steps 2 and 3 of hemostasis occur. So the second stage is platelet plug formation. This involves platelet aggregation. So you're forming a temporary platelet plug that seals the clot. So you have your platelet plug forming at the site of damage. These platelets are also going to, you can see they're kind of changing in their shape. They're also going to be releasing things that are going to help with the later stages of clot formation. So up here where this is undamaged, you have the platelets releasing. Let me get a different color here. The platelets are releasing here different, or the endothelial cells are releasing things like nitric oxide and prostaglandin or prostacyclin. These are preventing platelet aggregation, ensuring that clotting does not occur in healthy tissues. When the vessel is damaged, then you're going to have collagen fibers, so you're now exposing collagen here. These are going to actually be something that the platelets are going to adhere firmly to, and this is going to ultimately be enhanced by what is known as the von Willebrand factor, so the VWF. This helps to form a bridge between the collagen and the platelets, thus stabilizing the adhesion. Once this has occurred, the platelets are going to be activated. So you can see here is an unactivated platelet. It gets activated, and as it becomes activated, it is going to go through certain changes. So first of all, an activated platelet is going to swell. It's going to form spiked projections. This makes it stickier. And finally, it's going to release certain chemicals that are going to signal for platelet aggregation. So these include ADP, adenosine diphosphate. This is a powerful platelet aggregating factor. It attracts and activates more platelets. You have serotonin or 5-HT being released. This is going to help enhance the vascular spasm and promote further platelet aggregation. Thromboxane A2 is another chemical factor that is going to have similar effects to overall, this is going to really result in a positive feedback loop where activated platelets release more chemicals, which recruit and activate more platelets, thus leading to the formation of the platelet plug. The final step is coagulation. So the purpose of coagulation is to reinforce the platelet plug with fibrin threads. So you can see these structures right here, those are your fibrin threads. They are basically providing a molecular glue that stabilizes the aggregated platelets. This ultimately is going to form a blood clot. So this, all right there, that is the blood clot that is being made. So during this coagulation process, blood is going from a liquid to a gel, and this is going to happen because the dissolved proteins that are in the blood are actually forming the fibrin. So the fibrin was dissolved in the blood, but it essentially is going to be polymerized as different things are occurring. These different things involve clotting factors, so there are numerous clotting factors. Most of them are going to be plasma proteins, so proteins you find in the plasma that are made by the liver. You may hear of these referred to as factor 1, factor 2, factor 13. The numbers that they have are based on their historical discovery, not in the order in which they act. So that makes it confusing because you have factor 1 acting after factor, whatever. And so it's not a sequential thing. One thing that's important for the coagulation is vitamin K. So vitamin K is required to synthesize 4 of these clotting factors. It's not a clotting factor itself, but it is going to be necessary for the clotting factors to work. So the activation cascade involves several phases itself. So you have phase 1, which is going to be the production of the prothrombin activator. Phase 2 is where the prothrombin gets converted into thrombin. And then phase 3 is the conversion of fibrinogen to fibrin, helping to form the fibrin mesh. All right, so the coagulation pathways, there's actually 2 different. You have the intrinsic pathway and the extrinsic pathway, based on what is activating them. So intrinsic is coming from inside the vessel wall, while if you have damage to extravascular cells, that is part of the extrinsic pathways. Most tissue damage triggers both pathways simultaneously, although it is possible to trigger one without the other. They are going to share key similarities and ultimately converge at what is known as factor 10 or factor X. So things that are common to both pathways, both are going to require negatively charged membranes. Both are going to be so the reason they require negative membranes is because they need to be assembled on phospholipid surfaces, so that's necessary for the clotting to occur. Both are going to merge at factor 10. So factor 10 is a common point for both of them to merge. Activated factor 10 plus calcium and factor 5 on a phospholipid surface is what forms the prothrombin activator. So the prothrombin activator is going to be necessary. It is the slowest and rate limiting step of clotting, but once prothrombin activator is made, so that's this guy right here, the clotting process can occur in 10 to 15 seconds. All right, so the intrinsic pathway is required, or is called that because all required factors are found in the blood. So triggers include negatively charged surfaces, things like activated platelets, exposed collagen, or glass. So this is why blood will coagulate when you put it into a test tube. The intrinsic pathway is going to be the slower pathway because it has many intermediate steps. So you start with the damaged cell wall. This is going to expose collagen and activated platelets. Both of these things are negatively charged and will be enabling the coagulation process to start. So factor 12 is going to get activated into its active form, which is going to act as an activating factor for factor 11. Factor 11 is going to activate factor 9, and factor 9 is going to meet up with factor 8 to form a complex that involves factor 8 and factor 9 together. All right, so now let's take a look at the extrinsic pathway. So it's called extrinsic because it requires things that come from outside the blood, namely tissue factor, also known as factor 3. So this is an important one that I want you to know. Factor 3 is going to be released by damaged tissue cells surrounding the vessel. So you have your vessel, you have damaged surrounding it, it's going to be released, and now you have factor 3 in the vessel, leading to the triggering of this pathway. Factor 3 is going to be, or the extrinsic pathway is going to be the faster pathway. Notice that there's less steps here, so factor 3 is going to activate factor 7. Factor 7 then forms a complex with factor 3 and ultimately are going to continue on. And then we'll see that they converge at the formation of the prothrombin activator. So factor 10 here is going to merge both this complex and this complex, activate factor 10, thus forming the prothrombin activator. So this plus this is forming the prothrombin activator, which consists of factor 10, factor 5 in its activated form, phospholipids, and calcium ions. So that group there forms the prothrombin activator. So this leads us to phase 2, which is where prothrombin gets converted into thrombin. So this is the active form, and the key enzyme in driving the formation of the fibrin mesh. Then phase 3 is going to be actually that formation of the fibrin mesh. So the goal of it is to seal the injury. Thrombin is going to convert fibrinogen into fibrin. So this is soluble. Fibrin is insoluble. And so fibrin molecules are going to polymerize and form these strong cross-linked fibers. Factor 13 here, this is an enzyme that leads to this cross-linking. So you have your fibrinogen, that's factor 1. It is going to be activated by thrombin. So thrombin is going to convert the fibrinogen into fibrin. So these are the activated form of that. So these are polymerized, soluble, these are insoluble. And then factor 13 is going to take this and start forming the cross-linking that we get. And thus that is going to help perform the fibrin mesh that ultimately seals the wound until it's able to heal. During this process, you want this process to occur only when something is gone wrong. So blood clotting depends on a balance between the clotting factors and things known as anticoagulants. Anticoagulants being things that inhibit blood clotting. So you have both coagulants and anticoagulants in your blood. Normally, the anticoagulants are going to dominate, which prevents spontaneous clotting. But when the vessels are ruptured, then the coagulants are going to overwhelm the anticoagulants, and the clot is going to form. So anticoagulants are always there, but coagulants are going to dominate during tissue damage. So following the formation of clot, you have something that is known as clot retraction. So this is going to occur 30 minutes to an hour after the clot forms. This is going to help to strengthen and stabilize the clot. So platelets are going to contain actin and myosin. So you may recognize these from the chapter on muscle. They essentially are going to be able to contract. Notice that in that previous lecture I said that smooth muscle cells are the only things that have a contraction. Well, that's still technically true since platelets aren't true cells, but they do actually have a clotting or a contractile ability. So let's put some platelets in here. The platelets are going to pull onto the fibrin strands, and so this contraction is going to push the clot together. What this does, it helps to squeeze out serum. That's the plasma without the clotting proteins, making the clot more compact and draw the edges closer together, which is going to speed healing. While retraction occurs, the vessel wall is going to begin healing. So the platelet-derived growth factors, which come from platelets, unsurprisingly, so these are going to be secreting the platelet-derived growth factors, which stimulate fibroblasts and smooth muscle cells to divide. So the growth factor, you are going to have smooth muscle cells and platelets divide. Additionally, you have your endothelial cells. These cells are going to be secreting their own factors. So they're secreting vascular endothelial growth factor, or VEGF, which is going to stimulate other endothelial cells to start restoring the endothelial lining. This leads to a connective tissue patch that forms as the fibroblasts rebuild the area. All right, fibrinolysis then is going to be the next step. This is the process that is going to remove the clot. So the purpose, you have all these clots here. Ultimately, after healing has occurred, they're going to be unneedled. So small clots form continually in vessels. Without their removal, the vessels would become blocked. So we need to get rid of them. So the key enzyme here is plasmin. So plasmin is derived from the proenzyme plasminogen. So plasminogen is an inactive plasma protein. It is going to get built into the clot as it forms. The plasminogen then gets activated by several things. So you are going to have tissue plasminogen activator, or TPA. You're going to have thrombin, and you're going to have activated factor 12. So these things work together to activate the plasminogen, forming plasmin, and then because it's already in the clot, it's going to be restricted to the clot, thus causing the plasmin to break down these fibrin mesh fibers. So the plasmin then is going to break those down. Fibrinolysis occurs starting at about 2 days and gradually continues for several days until the clot completely dissolved. Now, this is restricted to the clot because plasmin that's in the blood is going to get destroyed. So I'll draw a face with 2 X's on there to indicate that the plasmin is destroyed. All right, so while clots are important to maintain healing, we don't want clots happening unnecessarily. So we do have things that are known as thromboembolic disorders. This is when you have a clot that is going to form and you're going to have problems with it. So a thrombus, this is a clot that forms and persists. So if it's a clot in an unbroken vessel, this can block circulation, leading to tissue death. You can see that going on down here. So you have a blocked blood vessel preventing blood flow. This is dangerous because ultimately blood can't get through there, and then those tissues are going to die because they don't get the nutrients and oxygen that they need. A thrombus that has broken free from the cell wall becomes an embolus. So an embolus is essentially a free-floating thrombus. It causes problems when it gets lodged in a narrower vessel. So an embolus in a narrow vessel can lead to what is known as an embolism. Risk factors, so roughened endothelium, slow blood flow, stasis can occur. They are going to occur. These are things that occur commonly with hypertension. And you may also notice that, like, if you sit for a while, you have slow blood flow that can lead to this clot formation. So that's why it's advised to not be sitting for too long of a period of time to get up and move around to make sure that the blood is circulating. Extremely dangerous forms of embolism include pulmonary embolism, which results in impaired oxygenation because your lungs need the blood it needs to get the oxygen to the blood, and the cerebral embolism, which can lead to a stroke. All right, so we do have drugs that help to prevent these. These are known as anticoagulants. So a few of them, aspirin is probably a very common one that you've heard of. It inhibits thromboxane A2, which prevents platelets aggregation and platelet plug formation. Heparin is a fast-acting injectable anticoagulant. It's used in hospitals for heart procedures or to treat preventable venous thrombosis. So it acts fast, but it does need to be injected. Warfarin is the preferred outpatient. So it's used to reduce stroke in atrial fibrillation. Warfarin works by inhibiting the function of vitamin K, thus reducing synthesis of the clotting factors. Warfarin is difficult to manage if you really need to balance this, because you don't want someone to have too little coagulation and bleed out, but you also don't want them to develop these clots that are dangerous. There are newer direct oral anticoagulants that use different mechanisms and are somewhat easier to manage, but historically these are three of the main ones that are used. So aspirin commonly will be used as a preventative measure. So you take a baby aspirin if you're at high risk for a stroke or a heart attack, or at the initiation of a stroke or a heart attack to help break up the clot. Inpatient heparin, because it's injectable and fast acting, is going to be used in hospitals, and warfarin is outpatient, but it is difficult to manage. Right, bleeding disorders. So one type of bleeding disorder is known as thrombocytopenia. So thrombo, that is referring to the clot, like a thrombus. Cyto, cell, and penia is referring to the fact that it's low, like in anemia. So here, thrombocytopenia, you have a low platelet count. This causes spontaneous bleeding, especially from small vessels leading to what is known as petechiae, that is small purple spots. What causes this can be anything that suppresses or destroys the bone marrow, since that's where platelets are found. So malignancy, radiation, certain drugs, and so you need to treat this with replacing platelets. So you get transfusion of the platelets. Impaired liver function can also be a case. So causes can range from vitamin K deficiency, hepatitis, cirrhosis, vitamin K issues. So if you have trouble absorbing vitamin K, that can also be a problem. Bleeding disorders such as hemophilia are also very severe. So there are several types of hemophilia, all linked to deficiencies in one of the clotting factors. So hemophilia A, this is the most common. It's a deficiency in factor 8. It is X-linked, meaning that you find it mostly in males because it is a recessive disorder, but males only get one copy, so they're going to be more likely to have problems with it. Hemophilia B, this is a deficiency in factor 9. It is also X-linked. Hemophilia C, this is a deficiency in factor 11. This is less severe and it is not X-linked, so it is found on a autosomal chromosome. The hemophilia C, it does seem to be result in less severe symptoms because they are going to be able to bypass this by factor 7 activation. So the symptoms of all of these begin very early in life. The characteristic of it is that minor trauma can result in prolonged and dangerous bleeding. This can result in repeated bleeding into joints, which can lead to painful, disabling joint damage. Treatment, so transfusions of fresh plasma and injections of purified clotting factors are two of the strategies. None of these are going to be long-term solutions, so you need regular injections or transfusions for both of these to occur. Both of them are inconvenient because you need to go in to get these, and the clotting factor one especially can be expensive. Blood transfusions. The initial loss to blood is going to result in what we refer to as shock. So the shock is going to be related to hypotension. Ultimately, you're not getting enough blood delivered to your different tissues. So loss of blood is going to be a life-threatening emergency if it becomes too severe. Shock is going to really come into play when you have more than 30% of the volume of blood lost. The restoring the blood volume is going to be important, but you also need to restore the blood cells as well. So Restoring only the volume helps with the hypotension, but it doesn't help with the replacing the actual function of blood, which is to carry the oxygen in the tissue. So that is can be a very important treatment option, but isn't going to be the only thing that is necessary. When you are doing blood transfusions, it's important to have compatible blood types. So the major blood types are type A, type B, type AB, and type O, and then you can have another factor in there with the Rh antigens, which is where you get the positive and negative from. So that's a different antigen, but it's basically the same principle as the A and B antigens. So if you have type A blood, you have A antigens there. Antibodies in the plasma, these are going to be anti-B. Typically, individuals will get exposed to this at some point in their life, especially if they've had a transfusion, and therefore are going to attack cells that are going to be damaged with that. Type B have anti-A antigens and the B antigen there. Type AB individuals have no antibodies in their blood and have both A and B antigens present, and you have anti-A and anti-B antigens present if you're type O, but no antigens present. So you have the antibodies present, but not the antigens. So who can you accept blood from if you are type A blood? You can accept blood from individuals that are type A or type O, because you have to look for ones that lack the antigens that they are going to have. So the anti-B antigens are there. These don't have anti-B, these don't have anti-B. You're good with both of those. If you're type B, you can get it from individuals that are B or O, because you're looking for individuals that have the A antigen, because that's what's going to be recognized. So here and here, you can't accept it from those. AB individuals can only accept it from individuals that are type AB, and then type O individuals can only accept it from individuals that are type O. So before you have a blood transfusion, you need to make sure that you have the correct type of blood to be transfused. All right, so that does it on blood. I'll see you guys next time.